41 through 44 is this stuff right here. Okay, 41 through 44 is this, and the most common, there's really two main errors that people make. The number one error, when we're doing this by the definition, right? This is what we learned yesterday, the definition of the derivative, and we're going to talk more about that here, but using this definition, what will be kind of today, for sure, will become known as the long way of doing the derivative. But when we're doing them by the definition, you're going to have one or two of those that you're going to have to do on the next quiz. And I mentioned that yesterday, and then I was very specific saying that there's going to be some problems on here where you have to do this the long way. I really expected to see a few more people coming in with questions. And then as I went around and looked, I'm thinking some of you probably should have spent a little more time asking about some of these things. Now we're going to talk about this. So the two things that really get people, number one, they just don't understand or remember or memorize the formula to the point that they can plug in and use it, number one. The second thing that people get in trouble with is just the algebra, right? You mess up the algebra. Now, how do you mess up the algebra? Well, one way to mess up the algebra is you don't plug in the right places, or you don't plug in enough or don't show enough work. I mean, that's very common. You guys are good students, probably went right through algebra and didn't show any more work than you had to. Many of you were that way. It's been that way ever since I taught this class. And I'm not going to say that you have to show every step like what I had there, but you are going, you have to understand how the points are allotted when I look at a problem. If this is worth 4 points, I'll probably say have something like 1 point for the initial setup, whether that's this step or whatever. Another point for showing where I can see that the H is canceled or something like that. Now, one nice thing about a quiz is I know you're not getting it any other way. This is a no calculator problem. If you get down and the answer is 1/8, well, how in the world did you get 1/8 without, kind of knowing what you're doing? So if you did some of that in your head, it is okay. I would just say that the most common mistakes, though, are made when you try to do too much in your head and you get, you just lose it. I'll be honest, like I said, I go around, some of you had your homework in about half a page, some of you had it in 3 pages. Well, I used to be one of those half a page people when I was doing math homework, right? And at some point, it was starting to burn me, and I was smart enough to figure out, well, maybe I need to do a little more when I need to. So that's the key thing. But you're going to have to do more of this today, right? For sure, on the homework and our next quiz, which is probably Tuesday of next week, we'll have some of this on it. So this was the one we did yesterday with the 2 plus h plugged in, because we're finding f prime of 2, and then we did this one too, where it worked out. Okay, so 41 through 44 was that kind of thing. I think number 7, you had to do that kind of thing. Number 7, as a matter of fact, you did this, except you had a -1 plugged into there. And so you had to go through all of this. All right, so let's talk about what we did yesterday. This is a little different version, but this is basically what you put in your notes yesterday. Algebra versus calculus. Slope between 2 points versus slope at 1 point. Slope of the secant line versus slope of the tangent line. Average rate of change versus instantaneous rate of change. A new term we came up with yesterday is the difference quotient. The difference quotient just means slope between 2 points. Here, the 2 points are A and B. Here, the way we wrote it yesterday, the 2 points are A and A plus H. Same thing, different notation. Over here, this is also the difference quotient. This piece of it is the difference quotient. Slope between 2 points. But then we add in the limit as H goes to 0, which is the thing that makes the 2 points become 1. Now I want to show you something I didn't show you yesterday, but that's basically not this one. This one, okay? So we start with a point right here. We would like to know the slope at that point A. So we create a second point, So we create a second point here, A plus H. We put that point on the curve, and that point would be called, the Y value of that would be F of A plus H. We draw the line in between those two. The green line is the slope between those 2 points. All right, And so the green line is the slope between those 2 points. Now, the limit as h approaches 0, h is this distance between these 2 points. So as we let h go to 0, sure enough, those 2 points become 1. And there's the definition of the derivative right there. There's the slope of the tangent line. The secant line turns into the tangent line. The slope between the 2 points becomes the slope at the tangent line. So, yesterday we had that. That's this definition. That's this red derivative. You have to memorize it. You have to be able to use it. Okay? But you also have to understand what it means. It would not be surprising to see a question on the next quiz that said, explain why this is the derivative of a tangent line. Explain why this is a derivative of a tangent line. Well, your explanation would use these two things right here. I think a good explanation would do that. You would just state that, hey, this part here is just slope between 2 points right here. This part is slope between 2 points, a and a plus h. This part, when the h gets close to 0, makes those 2 points get really close together and become 1 point. And that gives you the slope at 1 point. So you need to be able to memorize this formula. You need to be able to use this formula in this kind of long way of doing derivatives. And you also need to understand what it is. Okay? Why it's the slope. Why it's the derivative. Okay? Make sure you can do that. All right, so that's what we had yesterday. Then you had a problem like this. I think it was 13, kind of like this, where they told you let h be like 0.001 or something. Wasn't that 13? Right? So we still understand that, you know, we can do what we did in chapter 1, which is let 2 points get, you know, if we want to do the slope at 2, then we can just let the 2 points be really close together, like 2.01, and we can do a slope calculation. That's still average rate of change. It's the estimate of the slope. But what we learned yesterday is better than that, because what we learned by doing this is we can find the exact slope at 2. By letting the h actually become 0, letting the 2 points actually become 1, not just get close, but become 1. Because when the h's cancel right here, that's what happens. When the h's cancel, we can plug a 0 in for h. And we can let the 2 points become 1, and we can get the exact slope at 2, which would be 6. All right? So, but you still have to do problems like this. There'll still be problems that talk about average rate of change. On 11, parts A, B, and C, and whatever, it asks for the average rate of change on that graph. So you pick 2 points, do the slope between them. Right? You still got to know, when you hear average rate of change, that means slope between 2 points. Okay? All right, let's talk about number 43 in your homework. I want to do one more of these. We had 1 or 2 people go on yesterday, so I want to make sure you can see this. But I want to re-emphasize this process. We're going to do several of these today. So what was the function on 43? X cubed. And you were supposed to find f prime of 4. Okay? So, go back to this. Red definition. Now, what you notice is, if we're going to be finding f prime of 4, that means a 4 is right there for a. So that means a 4 goes right there, and a 4 goes right there. Now, people in the past that I have helped with this that had confusion about doing these the long way usually did not set them up right. They didn't get started right. Or they felt that they could do the algebra stuff in their head and they kind of skipped the setup part and then they got lost somewhere. So I always suggest to write out the F notation, because all you have to do to write out the first step is stick a 4 right there for A. So in this problem, what I would do, whenever I do these problems, I always start them out the same way. I say, okay, f prime of 4 is going to be the limit as h goes to 0 of f of 4 plus h. I just ignore the x cubed. I don't even care about it at the start. F of 4 all over h. I always do that part first, because that part never changes from problem to problem. All I have to do is put the 4 in for the a. What that allows me to do then is I can now look at each piece separately. Okay? Now, yesterday we did this. For those of you that were gone. We talked about, well, what's that mean, f of 2 plus h? Well, it means plug a 2 plus h in for x. Now, another common algebra mistake people make is they put the 2 plus h in here, but they forget to put it in for all the x's. Right? Well, when I put a 2 plus h in for x, you look over here at our example. Well, f of 1 means put a 1 in for x. F of 5 means put a 5 in for x, both of the x's. F of z means put a z in for x. F of peanut. What did we do yesterday? German shorthand. But f of peanut would be peanut squared plus 2 peanut. And f of 2 plus h would be 2 plus h squared plus 2 times 2 plus h. Now, if you want to try to do some of that in your head, go for it, but be careful. All right, so anyway, back to this. So now I can just say, all right, f of 4 plus h, that is 4 plus h plugged in for x. So that's 4 plus h cubed. Minus f of 4. F of 4 is a 4 plugged in. Now, I know 4 cubed is 64. I could have written a 64 right there, okay? But I'm just going to write that down and take it one step at a time. All right, now, limit as h approaches 0. Now, let's talk about this a minute. How do I cube 4 plus h? What's that? Okay, one way is to do 4 plus h times 4 plus h times 4 plus h. Is that what you were getting at? Okay, yes. That's fine. If you want to do that, 4 plus h times 4 plus h, maybe you can do that in your head. That's 16 plus 8h plus h squared. And then we're going to take that times 4 plus h. And all that means is you take 4 times everything, take h times everything. So 4 times everything, that'd be 64. 4 times 8 is 32h. 4 times h squared. Now take h times everything, that'd be 16h. That'd be 8h squared. And that would be h cubed. Right? And there you go. So that's all that. And then what was it? Minus 64. Then we're going to minus 64. Well, what happens? Beautiful thing right there. 64s are gone. Now I can combine some like terms. I've got 48h, 12h squared, h cubed. Right? Now, Kelsey and I were talking this morning about this. You guys remember this last year? Vaguely familiar? What comes next? 4, 6, because right, 3 and 3 makes 6. 3 and 1 makes 4. Right? 1, 10, 10. It's called Pascal's triangle. Pascal's triangle. Now, Pascal's triangle has all kinds of cool little things in it, but one of the things it has, and where I think Mrs. Payne did show this to you last year, is if I do a binomial expansion, meaning if I do x plus y to the 0 power, of course, that's just 1. If I do x plus y to the first power, that's 1x plus 1y, which is the 1 and the 1. If I do x plus y to the second power, that is x squared, 1x squared, plus 2xy plus 1y squared, 1, 2, 1. You see the pattern. These numbers are the coefficients in the expansion. Well, that could be helpful here, because if we have x plus y to the third, then that means that is going to be 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. Now you notice the 1, 3, 3, 1 from the triangle, and then the other pattern is the first thing is just cubed, then squared, then first power, then none. And the second thing in the binomial is none, then 1, then 2, then 3. So one goes downhill, the other goes uphill the other way. It's a quick way to do an expansion. Now, you might say, well, that took just about as long as doing this. I would agree. But what if you had fifth power? You're going to do 4 plus h to the fifth power and multiply all those out and add all those like terms? This could be a pretty fancy, nice thing to use. However, I'm telling you I won't go beyond third power when we do them this year, so we won't have to worry about it so much. But it could be a nice thing. You can get a college calculus professor who loves algebra, which they all do, and he would love to make you expand out a fifth degree binomial, right? So knowing Pascal's triangle is not a bad thing. So what would that look like if we do 4 plus h cubed? It would have been 1 times 4 cubed plus 3 times 4 squared h to the first plus 3 times 4 times h to the second plus 1 h to the third. Using Pascal's triangle, it would have been that. Well, 4 to the third is 64. 4 squared is 16 times 3 is 48. 12h squared, and 1h cubed. And you look at that, and you see that that's exactly what we had. Of course, once you subtract the 64, then you would be left with exactly what we had come up with. Okay, so that's something to have in your back pocket, I suppose, in case you ever needed that. Okay, so what do we got here? We ended up with, what did we say, 48h plus 12h squared plus h cubed. 3h cubed? Just h cubed. Okay, and so then what did we say we could do at this point? Take an h out. So if we take an h out, we got 48 plus 12h. I realize some of you, again, could look at this and maybe, see, all right, if I take an h out, what you're going to get. The great step that really is helpful right here is when the h's cancel, because let's not forget, let's not get lost in what was going on here. Why do we want the h's to cancel? Make the h be 0. When h is 0, the 2 points become 1. That's the great thing. But up here, if we tried to put a 0 in for h, we'd got undefined. We couldn't let the 2 points become 1. We couldn't let h be 0. But now that we cancel out those h's, we can. And so now we get limit as h approaches 0. We're left with 48 plus 12h plus h squared. When we let h be 0, that's gone, and our final answer is 48. That seems kind of strange. The slope, we're saying, of this graph at 4 is 48. Is that reasonable? Sure. X cubed. Think of x cubed. Goes way up really fast. You go out to 4, you're way up there high on that graph. Slope being 48 is reasonable. Okay? Don't forget what you were doing when you did this problem. You were finding the slope at that point. Okay? So that's what I want to see. Some, if not all of that work. All right. Next thing. Let me double check, make sure I'm on track here. All right. Let's talk about this real quick. Just kind of stop and process what we've talked about now. So I've got this function x squared minus x. First of all, as soon as you see that, let's try to imagine that in our head. What's it look like? X squared minus x. Parabola facing up. Okay, so we've got parabola facing up. How many different ways, or not, don't give me how many, but let's list some ways. Let's talk about some ways that we could find f prime of 1. Okay? So one way would be to do a slope calculation, pick 2 points really close together. This is what we did like on our last quiz, right? And plug those in. Now that wouldn't be the exact f prime of 1, but it would be an estimate. Somebody got another one? Somebody else got another one? Do this thing, okay? Do the thing we just learned, the definition. Okay, do the definition and find it exactly. Okay, what else? Tangent line. If we had a graph, if we knew what this parabola looked like, and let's say that was 1, we could come in here if we had a nice graph with some grid paper, right? If it was on a nice grid, probably, we could come in here, draw a tangent line. We could do a slope triangle. And that'd be an estimate too, but we could get an estimate that way. Okay, we could get on our calculator, zoom, 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 right? And we could do that. There's actually another way on our calculator. Let me show you that while we're talking about it. If you want to get your calculators out. But we could do this right here. On this button next to the 9, we're going to use that a little bit more today. What I'm about to show you, we don't hardly ever do, okay? Because we're going to come up with a shortcut today on derivatives, and so it's really faster to do it than do it with the calculator here. And the other times we need to do it, we usually are doing it in a no calculator situation anyway. So we don't use this very often, but it's nice to know about. So right here, this is the derivative. We're going to talk about this notation here in a minute. So I haven't shown you it yet, but this means derivative right here. Okay, so you're hitting this button next to the 9, and you're choosing that one right there. Now, what we do is we put an x down here, because we're going to tell it that we're doing the derivative with respect to x. And then we're going to type in this place, we're going to type x squared minus, what was it? X squared minus x. And then we're going to right arrow outside of that, and we're going to put the vertical bar. The vertical bar is right here if you hit control and then equals. Control and then equals, and you get this vertical bar. And then we're going to type x equals 1. Now the vertical bar means what? You remember? With or such that, right? And so what we're going to do is we're going to say we want the derivative, and I'll explain later why this means derivative, this notation. This is saying tell us the derivative of x squared minus x with x equals 1. So this is like saying what's f prime of 1. Okay? And so we hit enter, and it tells us the slope is 1. Okay? And that's what it would be if we were looking at this problem. Okay? So that's another way we can do it, is actually come in and ask the calculator to just tell us what it is. Okay? Again, that's not that useful. I can't think of it very many times we're going to use that. Matter of fact, a month from now, if I say, get out your calculator and show me how to do the derivative of 1, you probably won't be able to do it. Okay? Because we won't use it very often. All right. So that's just an interesting way to think about all the different things we've talked about with slope or derivative. All right. This you might want to put in your notes. Now we're going to come back to another homework problem. I still want to talk about 34 a little bit. I want to talk about 44 a little bit. Okay? Because it has some things we're going to need here. If you had any other homework questions outside of these, then you're going to need to come talk to me, look at the answer book, whatever. Okay? All right. So I'll give you a second to jot down this picture if you want to. What we're looking at here is an alternate version of the definition we learned yesterday. Okay? It's just an alternate version. Okay, I mean that picture doesn't have to be that fancy or anything, but all right, it's just an alternate version of the definition we learned yesterday. Now remember, the definition we learned yesterday was made up of 2 parts. First part was slope between 2 points, and the second part was the 2 points become 1. All right, slope between 2 points, and then the 2 points become 1, and that's the slope of the tangent line. That's the derivative. So here I have 2 points, a and x. Now yesterday the 2 points were a and a plus h. Okay? Matter of fact, I've got that. I'll come back to this in a second, but that's this right here. So I have 2 points, a and a plus h, and we were going to let the second point get closer to the first point. Let the right-hand point get closer to the left-hand point. It doesn't matter which way we go, actually, but we were saying let h go to 0. So we had the limit as h goes to 0, which brought the 2 points closer together. All right, well now in this version, I just call the point something different. I call one a and the other x. And I want the one on the right to get closer to the one on the left. So if you look what we've got here, if this point is a, then the y is f of a. If this point is x, the y is f of x. So if I subtract my y's, I get f of x minus f of a. If I subtract my x's, I get x minus a. And then the limit where the 2 points become 1 is I just let x get closer to a. So the limit as x approaches a. That's the difference. All right? So let's look at what that would look. It's just an alternate version. We don't see it very often. The one we learned yesterday is the one we see most of the time. But every once in a while this pops up. So we want to be able to handle it. We want to understand it. All right, so yesterday, let me write this in red. Yesterday, let's say this was, let's say the function was x squared. Obviously it's not. But let's say the function was x squared, and we were going to do f prime of 9. What would we have written yesterday? We just said the limit as h approaches 0. Yeah, let's do f of 9 plus h minus f of 9 over h. Now, when we actually wrote that out then, it would be limit as h approaches 0 of 9 plus h squared minus 9 squared all over h, right? And we'd have had that. And that would have been our limit we would have worked with. And then from there, we would have FOILed it. Nice things would have happened. H's would have canceled out. We'd have plugged a 0 in for h. And we'd have found f prime of 9. Okay? And it would have been some value. All right? Now, in this alternate version, if I want to do f prime of 9, the 9 would go right there, right? The 9 is the a, correct? So what would I have in this alternate version? It'd be the limit as x approaches 9. What would I put in for f of x? No. What's f of x? X squared, right? Now, oh, I see. If we want to actually do the f note, if we just want to leave it f of x, that's fine. We could go f of 9 minus, or excuse me, f of x minus f of 9 over x minus 9, right? Now, the next step, and that would be if we're going to show that step, which I don't mind. Okay, so this would be the limit as x approaches 9. Now, what would we substitute for f of x? It's just x squared, right? F of x is x squared. So it'd be x squared minus, and what's f of 9? 9 squared is 81 all over x minus 9. Now, what you'll see in this particular problem is this version actually is easier to work with than this version, because here we'd have to FOIL, things would cancel, factor out an h. This one's going to be real easy. What do we get? What can we do with x squared minus 81? X minus 9, x plus 9. Now, I don't think, there might be one of these in the homework. I don't think there is. X minus 9 is canceled. You end up with x plus 9. Well, guess what? Now we're doing the limit as x approaches 9. So what do you suppose we plug in? We don't plug in a 0, right? In this one we do, because we're saying that h approaches 0. So we plug it in for h. Here, x is approaching 9. So we plug in a 9. 9 plus 9 is 18. Well, guess what? That's the same thing we would have gotten over here. 81, let me just do it real quick. 18h plus h squared minus 81 all over h. The 81's cancel. We take out an h. We'd have 18 plus h. Plug a 0 in for h. We'd have got 18. Now, which one's easier? I don't know. But they both give the same answer. Okay? It just looks different. Just looks different. All right. So, this one over here is the one we'll deal with most of the time. This one, not as much. Now, we're going to learn today a little bit why we would do this one more. And over the next couple of days, we'll talk about it. But this is just an alternate version. Okay. Now, I've got some stuff here. I wouldn't write any of this down yet. I just threw a bunch of it up here. Now we'll talk about it kind of in order, and then you can write it down as we talk about it. So this is more notation. This is just more notation now. Because what we're getting to today is we're going to start talking about finding derivative formulas. Yesterday, I gave you this one, and everybody oohed and awed. Actually, you guys didn't ooh and awe that much. I was a little disappointed. But when we did the sine graph, and we said, okay, if f of x is sine x, and we plotted those slopes, and wow, it was a cosine graph. Remember that? How could you forget, right? So, and what we realized then is the slopes of the sine graph are the cosine y values. The cosine y values are the slopes of the sine graph. Kind of cool. Well, not only that, but that helps us. What we discover with that is we now have a formula for the f primes. So today's homework, where you had to find f prime of 4 in all those problems, right? I mean, let's go back to this problem right here. This problem. Yesterday we had this function, and we wanted to find f prime of 2, and we went through this whole long way of doing it. And then your homework on number 7, you had to do the same problem, except you had to do f prime of negative 1. You had to go through it all again. Well, if we wanted f prime of 3, we'd have to go through it all again. It'd be a lot nicer if we just knew what f prime of x was. Because then if I wanted f prime of 4, I could just plug a 4 in. If I wanted f prime of 3, I'd just plug a 3 in, right? It'd be nice to know what the formula is for f prime of x, not just the slope at one individual point. That's where we're going to head towards today. So I want to get you used to a little bit of notation. All right, so one way to write it is like that. Sometimes, instead of function notation, we'll use just y. So I might give you y equals sine x, and then we'd use y prime. Okay, so the prime notation is what we've learned so far with derivatives. And over here, for second derivative, right? F double prime or y double prime. Okay, so that's the notation we'll use most of the time. That's what we'll normally see for derivatives. It's good notation. But in the red, we've got an alternate notation. Now this notation will show up quite a bit. So this we should be familiar with. dy over dx is another way of writing y prime. It's the same thing. Now, where does it come from? Well, it comes from change in y over change in x. That little triangle is the Greek letter delta. So delta y over delta x means slope. Change in y over change in x. So dy over dx means slope, and of course that's what derivative is slope. Rate of change. So, that's what this means, dy over dx. Now, how you want to read it probably is like, you can just say dy over dx, that's fine. When we see it, we usually think in our head y prime. But just think derivative of y with respect to x. The x means that's your variable. It's kind of like f prime of x. It's saying this is the derivative of f, and x is your input. This is saying derivative of y, and the input is x. So again, it just means y prime. Now that's the notation your calculator used. If you go back to my scratch pad, it's that notation there. Now that's called Leibniz notation. Gottfried Leibniz, along with Isaac Newton, are the two guys kind of credited with discovering calculus. I mean, they're the ones that developed the ideas that kind of came together to be calculus. Now they did it separately, but they kind of they developed those ideas. Well, Leibniz is the one that used this notation for slope and derivative. Okay? So that's Leibniz notation. Now there's one great advantage to Leibniz notation, and here's where we'll use it a lot, is right here. Because one of the things we're going to do today is learn some shortcuts for derivative formulas. Okay? And when we want to write a list, because we're going to have to memorize them all, when we want to write a list of these derivative formulas, we're going to write them with Leibniz notation, because it's nicer than having to write it out this way. Instead of having to say, well, if f of x is sine x, then f prime of x is cosine x. What we can do is in one fell swoop, we can say the derivative of sine x equals cosine x. That's what that line is saying right there. It's kind of like we took the Leibniz notation here and took the y out. We just took the y out and replaced it with sine x. Well, that's what y is here, right? So we're saying, instead of saying the derivative of y with respect to x, we're saying the derivative of sine with respect to x. So the derivative of sine is cosine. That's what that line says right there. Okay, so I just want you to be comfortable with this notation. And then finally, this one down here. That just means second derivative. Those 2's there. They don't mean squared. Okay, they look like squared, but they don't mean squared. Okay, they mean second derivative. Now, the reason they look like squared is it comes from this. Since the second derivative is the derivative of the derivative, if we did Leibniz notation to do the derivative of the derivative, it would look like this, right? If this means the derivative of sine x is cosine x, then this would be the derivative of the derivative. Well, if you look at that, you can see where the d squared comes from, and you can see why the bottom would be like dx squared. So you can kind of see where it comes from. But it doesn't mean squared. It just means derivative of the derivative, which means second derivative. So when you see it, don't freak out. It's just the same as y double prime. We'll use prime notation most of the time, but that's just some notation, so be ready for it. All right, let's talk about 44. How many people struggled a little bit on 44? Raise your hand, don't be shy. Okay, fair enough. Now, the struggle was, I'm guessing, the algebra. Okay, here's the function. Now notice how I've already set it up. I've started it the way I start every one of these problems. is I wrote out the F notation for my derivative rule that I've memorized. Okay? So limit as h approaches 0. Since I'm finding f prime of 4, I just put a 4 in for the a. That's all I did. Okay. Now I need to do the red part. What's f of 4 plus h? What's f of 4 plus h? 2 over 4 plus h. Right? F of 4 plus h always means take 4 plus h and plug it in for x. So we do. And then minus the other red part. F of 4. What's f of 4? 2/4 or 1/2. And that's all over h. So now we have to do some algebra to this. Well, this is not factoring and canceling and that kind of thing. This is a different type of algebra. There are 3 algebra techniques you have to know for this next quiz. One of them is the one we've been doing, where things FOIL out, terms cancel, and you can plug a 0 in for h. That one you have to be able to do. That's the one most of them have been so far. Here's the second of the 3 you have to be able to do. You have to be able to do a fraction in a fraction like this. Question? No. Okay. So how do we do this? What do we do with this? If you're in Mrs. Payne's class, and Miss Payne loves the bow tie. Loves the bow tie. Now, all the bow tie is get a common denominator. Get a common denominator. You cannot subtract, you can't cancel these h's, number one. Don't try that. You cannot, the only way to do a fraction inside of a fraction is to get this into one fraction up on top. You've got to subtract these fractions. The only way to add, subtract fractions is to get a common denominator. Now, how many people have never heard of bow tie? Raise your hand. There's plenty of you in here, I'm sure. I know there's more than one, but that's okay. All right, some of you are afraid to raise your hand. Whatever. Well, until Mrs. Payne started teaching advanced, I'd never heard of bow tie either. So we're in good company. All bow tie is get a common denominator, but it's a pretty cool way to do it. I like it. Okay, so let me show you what get a common denominator is. The common denominator is just this times this. 4 plus h times 2. So what that means is I'm going to take and multiply, whoops, let's get some red in here. I'm going to multiply this bottom times 4 plus h, and I'm going to multiply the top times 4 plus h. That's a well-chosen one. This is not bow tie. I'm going to show you bow tie in a second. That's called a well-chosen one. I'm just going to multiply this times 4 plus h. On this one, I'm going to multiply the top and bottom times 2. So all I did is that way that gives me a common denominator. Now, what the bow tie method is this. Now, one of the things I don't like about bow ties, it looks like cross multiplying. Those are two different things. Cross multiplying is when you have an equal sign in between when you cross multiply, so keep that straight. But it looks like a bow tie, right? So bow tie means you take this 4 plus h times that 1, and so up here you have a 4 plus h. There's a minus sign there. And then you take this 2 times this 2, and that goes over there, and that's a 4. Now, if you look at what I was going to do, it's the same thing. So I took 4 plus h top and bottom, I get a 4 plus h here. I take 2 top and bottom, I get a 4 over here. Same thing. Now you got to remember that's over then the 2 and the 4 plus h multiplied together. Right? That's these things down here then multiplied together. Okay? Well, I was going to get that same thing, if I do the common denominator. So I don't care to do it bow tie, common denominator, whatever. You've got to be able to do this algebra technique. All right, now, the other thing I got to be careful of is I didn't put parentheses around this. When we minus this 4 plus h, that has parentheses around it. So I'm guessing if you had 1/8 as your answer, you messed this up because it should be negative 1/8, right? You lost track of that negative sign because you did not distribute that negative, and this is where people who don't like to show a lot of work get in trouble. Okay, is that right there? Because they do that in their head. And they say, oh, the 4's canceled, and then they leave that h. So really what you have here is 4, So really what you have here is you have 4 minus h all over 2 times 4 plus h. Now, I could have distributed that 2 through there. Sometimes we don't like to because things may cancel, so I don't like to distribute if I don't need to. But in this one, it turns out we probably will. Okay, we're still not done. Obviously, the 4s are going to cancel here. So we still have this negative h over, and I'll go ahead and distribute that. That's going to be 8 plus 2h. And then that's all over h. So if you've been able to keep up with it so far, if you've been able to get that common denominator bow tie, get the 4s to cancel, which is actually a good thing, you get to here. Now what? The h's do cancel, but we got to be really careful with that when we have a fraction within a fraction. Why do the h's cancel? Because if you have a fraction over another fraction, the top can cancel the top and the bottom can cancel the bottom. That's right. So that's an okay way to do that. Now, why is it that way? If you've never heard of that or can't remember that, think of it this way. We're dividing by h right here. Dividing by h is the same as multiplying by 1 over h. So dividing by h is the same as multiplying by 1 over h. And that's why then the h's can cancel. Okay? So you've got, I call that invert and multiply. If you're dividing a fraction with a fraction, take the bottom one and invert it and multiply in the top. You're multiplying by the reciprocal. Okay? And so look what happens. That h cancels that h, and we end up with negative 1 over 8 plus 2h. Now that's a beautiful thing because remember, we want to be able to put a 0 in for h. Well, everywhere up until here, we'd have been dividing by 0. But now, even though there's an h in the bottom, it doesn't matter because now we can put a 0 in for that h because there's other stuff down there. So we put a 0 in for that h and we get negative 1/8. And there's our answer. Okay? Now, let's think about what this was. I don't know if any of you know what the graph of 2 over x looks like. It is one of those graphs we should know because it's a graph of 1 over x with just a 2 on there. It's this graph right here. It's a hyperbola, actually. 2 over x is this graph right here. It's a hyperbola in the first and third quadrants. Okay? Well, out here at 4, does it look reasonable that the slope would be negative 1/8? Pretty flat and going down. And there it is. Okay? So that is an algebra technique we need to know doing this. All right? You're going to get a chance to practice that on one of your homework problems for tomorrow. All right. Now, so since we just came up with that algebra technique, and I told you there were 3 of them that you have to do. We're not going to go through this one because we just did it, but one of them is getting a common denominator bow tie. That would be an example of a bow tie common denominator kind of problem right there. We would need to get the top put together as one fraction with a common denominator. And then some things could simplify from there. So you've got to be able to do that. The third of the 3 algebra techniques we need, we're going to do right now. And it's called the conjugate method. Now the conjugate method is used when we have radicals. Okay? Here's what the conjugate method is all about. A plus b, the conjugate is a minus b. Conjugate of a plus b is a minus b. Or the conjugate of a minus b is a plus b. When you multiply those two things together, something really nice happens. What is it? The middle part cancels out, and we get a squared minus b squared. Now, the beautiful thing about that is when the things that you end up with are squared. Well, if you're dealing with radicals, square roots, and you square them, the radical goes away. So being able to multiply by a conjugate is often a nice thing to get rid of radicals. Now for us, it's going to make some things cancel out. Where you've seen it before would be in an algebra problem. Mrs. Andreessen does not like to see square roots in the bottom of a fraction. Right? Rationalize the denominator. We got to get rid of that. What do? We multiply by the conjugate. So you got radical minus 2. We're going to take radical plus 2. And we got to do that times the top and the bottom. So on top we would get 3 and then radical x plus 2. I didn't distribute those because usually when we do this we're hoping things cancel. So I like to leave them factored until I know that they're not going to cancel. And what do you get on the bottom here? X minus 4, the radical is gone because we get radical x times radical x, which is x. The outers and inners would disappear, and then negative 2 times 2 is negative 4. And for algebra class, what's happened is we have now got the radical out of the bottom and in the top, which is what they like to see happen. Now for us, it's not going to be that. When we do it, it's going to help something cancel. It's going to help those h's cancel somehow. Okay? And we're going to be able to then figure out and let h be 0. But you need to recognize that. So if you get into a problem that's got a radical in it, you want to multiply by the conjugate. So you have radical plus something, you want to multiply radical minus something. Or if you have radical minus something, you'll multiply radical plus something. Okay? And you'll have one of your homework problems where you have to do that. So 3 algebra techniques: factor and cancel, conjugate, get a common denominator. Okay? All right. Let's talk about number 34, and then we'll stand up and stretch for a minute. All right, 34. First of all, I'm going to rewrite this. This looks a lot like what we've been doing, except this delta x is where what normally is, the h. So I'm going to rewrite it. I'm just going to change that to an h. And actually, I'm going to change the 3 also. I'm going to change the 3 to square root of 9. Now, you're going to wonder where in the world I got that, but you're going to see why that's important here in a second. Okay? The 3 is the same as square root of 9. Now, once you see me do that, you probably say, oh, yeah, okay, now that does look a little more familiar. Okay? Now, here's what this problem is. This problem is saying, I think in the directions, they say this limit is f prime of some a for some function f of x, which you're supposed to figure out, and for some a value, which you're supposed to figure out. So it's kind of like you're supposed to go backwards from what we've been doing. So I'm going to back up and go back to this problem right here. So what we have in this particular problem is this green thing. No, actually, I'm sorry. We have this green thing over here, right? In our problem right now, we have this thing right here looks a heck of a lot like this green thing right here. Limit as h goes to 0. We got a 9 plus h. We got a 9, right? Now, where did this 4 come from? The a, right? Right? The a. It came from right there. So in our problem, what do you suppose the a is? Back up here. 4 plus h, right? The derivative is f of a plus h, right? So what do we think the a is? A plus h, 9 plus h. So it looks to me like this is the a right here. Because isn't it f of a plus h minus f of a? That's right. Yeah. So doesn't this have to be the 9? So I think this was f prime of 9. And I think the a, yeah, the a is a 9. So you're supposed to identify the a. Now what was the function? What was the function? Well, let's go back to this one. The function here was x cubed. You see where that came into play here? Remember how we've been saying the German shorthand thing, f of 4 plus h? 4 plus h is where we plug that in for 4 plus h, we plug in for x. Boy, we need that break. Okay, it's coming. Hang in there. 4 plus h, we plug in for x. 4, we plug in for x. So wherever we see the, look at this now, listen carefully. Where we see the 4 plus h is where the x must have been, because that's where the 4 plus h gets plugged. So wherever the 4 plus h is must be where the x must have been. So this must have been x cubed. So in this problem, what must have been our f of x? Square root of x. It's that easy. Because where the 9 plus h is must be where the x was. Because that's where the 9 plus h goes. When we have f of 9 plus h, we plug it in where the x was. And then we plug the 9 in where the x was. So there must have been x there. This function must have been square root of x. So what this thing here is the slope of this square root of x graph at 9. Now I'll show you real quick what the square root of x graph looks like. It's a sideways parabola. And out here at 9, it's got a pretty darn flat slope. Well, I'm going to run through this one real quick for you because this brings up the conjugate thing we were just talking about. So if I gave you this problem, and you're going to have one similar to it tomorrow, and I told you to now work this out with algebra, there's nothing to factor and cancel. There's no common denominator. What we're going to have to do with this one is we're going to have to take the top times the conjugate, which would be square root 9 plus h plus, let's quit calling that square root of 9 now. Let's call that 3. You see how that's the conjugate? I'm going to multiply, I got radical minus 3. I'm going to multiply by radical plus 3. And I got to do that to the top and the bottom. So this is what that conjugate thing we were just talking about would look like. Now, what do you get? When you FOIL the top, what do you get? The radical disappears. Minus 9. That's awesome. Look at that. You can see what's going to happen. The bottom is kind of messy, so I'm not even going to distribute it. I'm just going to go 9 plus h plus 3 like that. Look what happens when you do that conjugate. The 9s go away. The h goes away because now you got h cancel h. And you end up with 1 over square root 9 plus h plus 3. And then remember, h goes to 0. So 9 plus 0 is 9. The square root of 9 is 3. 3 plus 3 is 6. You get 1/6, which is perfectly reasonable for the top half of a sideways parabola out at 9 for that slope to be about 1/6. Okay, so now you've seen the conjugate method. You've seen the common denominator method. We've done the factor cancel. That's what those look like. Okay, stand up and take a minute break here. Yep. And stretch. All right, let's have a seat. What is a room no one can enter? A mushroom. Where do astronauts leave their spacecraft? Mushroom. At parking meteors. All right. Thank Kelsey Stithen for giving me that Laffy Taffy today. All right, here we go. So, and she wasn't even in here to hear. All right. So, notes. In your notes, what kind of room can no one enter? This is off that Laffy Taffy you gave. I don't know if you gave it to me. You left it in there. The one that was frozen. A room no one can enter. A mushroom. Okay. I didn't want you to miss it. All right. So now, what we want to do is we want to take this a step farther. What I was talking about earlier is we want to get a derivative formula for, we want to start getting some shortcuts for doing things this long way. Okay? So we're going to do one right now. So we're going to start with the function x squared. Okay? And what we would like to do now is we would like to find not f prime of 3, not f prime of 4, not f prime of -1. We would like to find f prime of x. We would like to find the slope for any point x instead of a specific point x. Because if we knew the formula for f prime of x, we could then just plug in numbers in for x. It would be a much nicer way to go. Well, that's going to be very similar to this. Matter of fact, I have it up here. If you look at this and look at this, what's the difference between these two pictures? All I'm going to do is I'm going to change the A to an X. Now, what's the difference? There is no difference. The only difference, I guess you could say, is obviously A and X, there's a difference, but A represents, use A to represent a specific point, like 2 or 3 or 4, and we're going to use X to represent any point. But when I go through and create this, it's all going to be the same, right? Your definition is going to be the same. The only difference is instead of an A there, we'll have an X there. And that's it. So, to be honest, from this point forward, when we talk about the definition of the derivative, you'll probably see me write it this way now with the X instead of the A. It's not a big deal. If I want to do f prime of 3, I can put a 3 in where the X is, right? If I want to do f prime of 3, put a 3 where the X is, put a 3 where the X is, put a 3 where the X is. And it's the same thing we've been doing. So it's not a big deal, okay? So, but this is probably the version we'll probably see more now than the one with the A. Because this is more useful. It'll let us do at a specific point if we want, but it'll also let us do it just for any old X. All right, so I want to find f prime of x. So here we go. So I've got it set up here. What is f of x plus h then? Okay, see, you guys are too good. You're better than me. I can't do that. I got to show this. But you're right. Isn't it going to be x plus h plugged in for x, right? Isn't that what this means? Think German shorthand here. F of x plus h means take x plus h and plug it in for x. All right, minus the other red thing. What's f of x? That's just x squared. And then all over 8. So see how we're doing the same thing, except instead of having 4 plus h or 2 plus h that we're plugging in, it's x plus h. That's the only difference. Only difference. Okay, so away we go here. We got limit. Oops, forgot to write it last time. So we FOIL this. We get x squared plus 2xh plus h squared minus x squared all over h. The x squareds cancel, correct? Which is nice because now what? That was numbers before. That was like 64 cancel 64, but now it's x's, but that's fine. Now what? Now I can take out an h. We get 2x plus h over h. The h's cancel, which is awesome because now I can put a 0 in for h, right? And that gives me 2x. So what I just learned is that if I have f equals x squared, f prime is 2x. Now we had already thought that when we had a parabola as an f, remember we matched those graphs? When we had a parabola f, we had a line for f prime. And it turns out That's actually what happened. Okay, let's do one more real quick. Let's start with x cubed this time. Some of you may be seeing what's happening, and I don't say anything just yet. But on this one, and the two you're going to do this long way today in your homework are going to be this way with x's in them. Okay, so again, I got f of x plus h minus f of x all over h. Started out that same way again, except this time now, what's f of x plus h? It would, well, I can't do that much in my head. What's that mean, f of x plus h? Oh, there, okay, maybe that's what you said. I'm sorry, maybe I didn't hear that. X plus h cubed minus, and then what's this red thing? What's f of x? Just x cubed. All over h. Now, it's a good thing that we learned that we reviewed that Pascal's triangle, because that's going to come in handy right now. I'm going to use it. So let's expand x plus h cubed. Remember it? 1x cubed, 3x squared h, 3xh squared, plus h cubed, right? That would be the binomial expansion of x plus h to the third power. And then minus x cubed, which, awesome enough, the x cubes cancel. Leaving us something on top that can happen, which is take out an h, gives me 3x squared plus 3xh plus h squared. Did I do that right? All over h. Cancel an h. 3x squared plus 3xh plus h squared. We let h be 0. We just learned that if f of x is x cubed, that f prime is 3x squared. Look at that. So now if I wanted f prime of 4, what do I do? No. If I wanted f prime of 4, what would it be? Actually, we did this already. Problem 43. It'd be 48. Remember that? Problem 43, we plugged that in, 4 plus h, I don't think we got 48. All we'd have to do now is put a 4 into that formula. 4 squared 16 times 3 is 48. Much easier, right? Much easier. Now, you say, well, where would this end? Well, I'm hoping some of you see it already. If not, we're going to have to go through this. If I tell you that f of x is x to the 4th, can you tell me f prime? Did you see that pattern? Did that pattern hold back here? Yes, it did. That's pretty cool. And where did that come from? It came from Pascal's triangle. It came from binomial expansion. It came from slope between 2 points. It came from the 2 points becoming 1. It came from a bunch of algebra. But in the end, look at that result. There it is. We just learned our first rule, rule that we can use for multiple functions. We already talked about the sine function. The derivative was cosine. We talked about e to the x. The derivative was e to the x. We just learned something called the power rule. The power rule. Now I'm going to use Leibniz notation for this. The power rule says that if you have x raised to some numeric power n, now this doesn't work for e to the x, it doesn't work for 2 to the x, it works for x in the base raised to a numeric power. That's important that you understand that difference. The rule is what? N goes out in front times x to the n minus 1. That is the power rule. We bring the power down in front, and we drop the power by 1. This is going to be really useful. There's a lot of polynomial type functions that are x raised to a power. We can now, now you can see why we call this the long way. And we now have kind of a shortcut rule for doing the derivative. Now, in some of your homework, you're going to get to use, we're going to practice using this shortcut, these rules. Okay, there's a couple you're going to work out this long way. So you practice some of that algebra we've talked about. But there's a bunch of them you're going to get to do with this shortcut. Okay, so let's go through some of these. What just happened here? Oh, okay, I skipped a slide. All right, we're going to go through some examples here of how this shortcut can be put into action. Okay? How this shortcut can now be put into action, because we know we don't normally have functions that are just x squared or x cubed or x to the fourth. They usually have a shift or a stretch or some other stuff going on. Okay? So how can we deal with those? So let's talk about this. So I just made a little chart here of some examples that we're going to run through. Okay? All right. So the left column is f. The right column then is f prime. So let's say we have excuse me, a power, and it is shifted 4 to the right. Does that change the slopes? But does it change where they are? Yeah, if you shift the graph 4 to the right, it doesn't change the slopes, it changes where they are. For example, if you had a peak that was back here at 2, x equals 2, and you had a peak where the slope was 0. Now you shift that graph 4 to the right. Now where's the peak? At 6, right? If it was at 2 and you shift 4 to the right, it's now at 6. In other words, the derivative has to be shifted 4 to the right also. Okay? So, what's this derivative look like? We bring the 5 down in front, just like we said. We leave the inside alone because it has to be shifted 4 to the right also. We drop the power by 1. So we use our same power rule, but we have to have that shift in there. Now, I said something there that you're going to hear me say a lot. I said, we leave the inside alone. Because that happens all the time when you're doing a derivative. If you've got something on the inside, we're going to see in some examples here. If you've got something on the inside, you do the derivative will also have that same inside. You leave the inside alone. There's no time when you would not. Okay? So we just do our power rule, we leave the inside alone. All right, now we got this problem. Now we got that 3 sitting there. What does that do to the graph? Shrink. Horizontal. Horizontal shrink. Does that change the slopes? It has 2 changes to the slope. Number 1, it changes where they are. All the slopes, if you had a slope that was here and now it's shrunk in, it's now shrunk in. And it's also steeper. Right? And it's steeper by what factor do you suppose? By a factor of 3. So, here's what has to happen here. We're going to bring the 6 down in front. We're going to leave the 3 on the inside and make that a 5. But we have one more thing we got to do. Okay? On the first one we did, we shifted 4 to the right. It didn't change the slopes, but it just moved where they were. So our derivative had to have the move in. Here, when we shrink the graph, when we compress the graph, it changes where they are, which is why we have to leave the 3 on the inside, but it also makes them 3 times as much, 3 times steeper. So we have to actually kick out and multiply by a 3. So when we have a multiplier on the inside, it compresses and makes those slopes bigger by that amount. So we have to kick out a multiplier. So this answer would actually be 18 times 3x to the 5th. Okay? Now, while we're at this, we might as well go back to our calculator. You don't have to do it on yours. I'm going to show you here real quick. This derivative thing we had here actually will not only find the derivative at a point for us, but because of the CAS, it will find the derivative at any point for us. In other words, in terms of x. All I have to do is leave off the vertical bar part. So if I do the derivative of, and let me put an x down there, tab, And let's just do the one we did a minute ago, which was x cubed. Let's do x cubed. And sure enough, there's a derivative, 3x squared. That's pretty cool. That's what CAST does for you. The ones that aren't CAST, it won't do that. Okay? Now we go in here. Let me do that derivative we just did. So we can check our answers. So we can go in here and say, okay, what if I had parentheses? X minus 4 raised to the 5th power. Look at that. It gives me that derivative. Okay? One more here real quick. So you can use your calculator as kind of an electronic solutions manual, I guess you might say, where you can go in here and you can check these. Now let's do a parenthesis. Let's do 3x. Let's go outside the parenthesis, raise that to the, what do we have, 6th power. Now, unfortunately, that time it didn't leave the 3 on the inside. It went ahead and distributed and multiplied it all out. So what I could do is, if I want to check my answer, I'm like, oh, that's not the answer I got. Well, what I can do is I can just type in my answer. So I'll go 18. Now, wait a minute. I got this, 18 times 3x in parentheses, and then raised to the 5th. That's what I had. And I hit enter. And it's like, oh, yeah, okay, they're the same thing. So I was right. Right? So you can use your calculator to check these things. Now, when we do a quiz, we're going to do a big quiz. This doesn't come until chapter 3, so it's a wise way. But where we're going to have to be able to do all these different types of derivative rules we're going to be learning. Of course, you can't use a calculator because that would be easy. Then all you have to do is type them in. Okay? But it's when you're studying for that, you're practicing for that, you can certainly use your calculator to see if you're on the right track. Okay, let's keep going. Sine of 2x. Now, we already learned that the derivative of sine is what? Cosine. And we also learned that we leave the inside alone. So the 2, again, compresses that graph. So we have to leave the 2 in there because it's going to compress those slopes in there. But it also makes the slopes what? Steeper by 2. So we have to kick a 2 out to the outside as well. Because what's going to happen is that is going to make those twice as steep. So we have to kick a 2 out. Now again, if we don't believe it, I guess I would do one more for you here. If we go in here and we ask for the derivative of sine 2x, and we hit enter, sure enough, you can see that it kicked out that 2. Okay, but I want you to understand why it kicked out that 2, because of the steepness thing. Okay, what about a 3 on the outside? Vertical stretch, does that make them steeper? Sure, by a factor of 3. So what that means is we have to have a 3 on the outside, and then the derivative of sine just cosine. So all that tells us is if you have something on the outside, it's just going to hang out there. If you have a number multiplied on the outside, you're not doing anything special with it. It just stays out there because it's stretching those slopes, and so the slopes will be 3 times as big. So a number multiplied on the outside of the function, it just hangs out there. And then we do our derivative like normal. So the derivative of sine is just cosine. So it's the one on the inside that's tricky. We have to keep it on the inside, and we have to kick out that number as well. All right, what's the derivative of 7x? Wouldn't it just be 7? First of all, it's just a line. And what's the slope of the line 7x? 7 all the time. So the derivative's got to be 7. But if you do our power rule, bring the 1 down in front. 1 times 7 is 7. And then change that to x to the 0. X to the 0 is 1. And so we do get 7. So the rule still works. What's the derivative of 5? What's 5 if you graph it? Horizontal line. What's the slope of the horizontal line? 0. So any constant, the derivative is going to be 0. Now, does that fit the rule? Well, actually it does. You say, well, there's no x there. How can it fit the rule? Well, there is an invisible x there. It's x to the 0. 5x to the 0 is the same as 5. If we bring this 0 down in front, well, enough said, right? You bring the 0 down in front, it's going to be 0 times all that. It's going to wipe it out, and it's going to be 0. Okay? So it does fit the pattern. But a constant horizontal line, slope is 0. Just remember it that way. Okay? We're not done. Hang in there. That's why I let you stretch. We're almost there, though. I can have a lot of homework time. Apologize. Sometimes we have those days. All right, here's the next one right here. 1 over x cubed. Nice thing is, it's going to make your homework go a lot easier, though, that we went through these. 1 over x cubed. That does not fit our rule because our rule is only for x raised to a power, so we have to rewrite it. That's why I have the arrow here. 1 over x cubed is what? That's right. So we have to rewrite these. So sometimes we get to a problem, we have to do some rewriting. We have to rearrange it so it will fit our rule. Okay? And you're going to have some of those in your homework. You might have to FOIL out some parentheses or something before you can use the rule. Now, what's the derivative using the rule then? -3. Careful. -4. You've got to subtract 1, right? The rule says you take away 1. So -3 take away 1 is -4. So be careful there. Okay? What about square root of x? All we have is a power rule right now. We got to write it as a power. This is earlier in the year I told you whenever we have radicals, we'll write them as powers most of the time. Well, here's a big reason why. Is because we have this great rule about powers and derivatives. So we want to write them as a power. So what is this derivative? 1/2 x to the -1/2. If you take 1/2, take away 1, that's -1/2. You're going to have to be able to work with some fractions. Now, if you check this on your calculator, it's not going to write it that way. Your calculator is going to do this. Now, this is some algebra you have to be able to do, but don't worry about it right now. I'm not going to make you rewrite this, but the negative power means it could go to the bottom. X to the 1/2 is the same as square root of x. So this would be 1 over square root of x, and when you put that all together, it's 1 over 2 square root of x. If you type in the derivative of square root of x into your calculator, it's going to give it to you this way. I'm perfectly fine with you leaving it as a power. That's fine. I know Ms. Andreessen, I think the rule was this. If the problem started as a radical, she wanted her answer to end as a radical. If it started as a power, end as a power. For us, we don't care. We usually leave them as power. But if I had to plug in a 9 right now and I didn't have a calculator, would you rather plug a 9 into this or that? I'd rather plug a 9 into this. So if I needed to do this, I need to be able to. But you may not have to. Okay, depends on the problem. All right, what about cube root of x to the 4th? That is x to the 4/3. That's right. That is x to the 4/3. The root is the bottom. The power is the top. So that derivative would be 4/3 x to the 1/3. 4/3 take away 1, 4/3 take away 3/3 is 1/3. All right, a couple of other quick little notes and then we'll be finished. If you have a string of terms, you can do each one individually. Now, seems like a no-brainer. Well, it's not when we get to this bottom one. I'll show you. But on this one, we can just do the string of each one. So we bring the 4 down in front. That would be 12 x to the 3rd minus 6 x squared. What's the derivative of 8? 0, right? Derivative of a constant is 0. So the derivative of 8 is 0. So there would be the derivative of that one. Those numbers in front, the 3, the 2, they just hang out there. Remember we said that. The numbers in front, they just hang out there. Okay? Now, this one. Can we do the derivative of each one individually? Well, sure be nice, but it turns out we can't. When we're adding or subtracting a string of things, we can do each individual derivative. But when we're multiplying or dividing things, we can't. Now, there's a quick way to show you. Let's pretend we could. So you might think, well, I would do 3x squared, and then I would do 4x cubed, right? We might think that would work. Well, we know when we multiply that together, that's 12x to the 5th, right? Well, we also know that x cubed times x to the 4th is x to the 7th, right? Now, what's the derivative of x to the 7th? We know that's 7x to the 6th. Well, that is not equal 12x to the 5th. So, unfortunately, when we're multiplying things, we cannot just take their individual derivatives. We need to multiply them together and do something with them. Now, don't write this down, but here brings up this one then. So what would you do if you had something like this? Well, we're not going to do this right now, but the hope would be you could do this derivative, then this derivative. It turns out you can't. You can check it on your calculator. It gives you something different. We will learn that later, probably next chapter, actually, what we do with something like this. Okay, so when you're adding things together, you can do each individual derivative. When you're multiplying or dividing things, you can't. You have to do something special. All right, for your homework, if you look at the assignment sheet, it says 2.2 on pages 98 to 100. Now, I think most of these problems are shortcuts. Okay? Most of page 2.2 is some functions, and you get to use this power rule. Now, you might have to do some rewriting like some of the ones we were just doing, but you're going to get do the shortcuts. So there's not a lot going on there. Those don't take very long. Okay? So that's that part of it. Also, then you notice on your assignment sheet below 2.2, it says do the derivative by the definition. So that's the long way. Do f of x equals square root of x. So that's going to give you practice with that conjugate that we talked about. And do f of x equals 1 over x, which is going to give you some practice with that common denominator. But what you're doing there is you're doing just like we did with x squared and x cubed. When we did x squared and x cubed, we weren't doing f prime of 2, f prime of 4. We were doing f prime of x. That's what you're supposed to do for those two. Now, you already know what they're going to be because you know we just did this one. X to the 1/2, we know what it should come out. This is x to the -1, our shortcut. We know what it should come out. But you've got to go through and do them the long way and show that they do come out that way. And if you don't remember what I'm talking about, that was right back here. Right? When we did x cubed, came out 3x squared. When we did x squared, came out 2x. That's what you're doing. Okay? For those two problems there. So, bunch of them with the shortcut on page 98 to 100, and then those two with the definition. All right, you can have the last minute and a half.